Hello AP Statistics students. In this video, we are going to do a two-sample z-test for a population proportion. So far, we've only been doing one samples, right? Now we're looking at two samples. The difference here is very, very similar to when we did this same idea for a confidence interval. We did one sample confidence intervals and then we did two sample confidence intervals. Some of the differences are very similar, and hopefully you will see that the two procedures are very similar. The main thing we have to do is identify these problems as having two populations and two independent samples. Then you'll know what the correct procedure is to do. So let's take a look at this. Researchers designed a study to compare the proportion of children who come to school without eating breakfast in two low-income elementary schools. An SRS of 80 students from School 1, all right, I'm going to highlight that right there. An SRS of 80 students from School 1 found that 19 missed breakfast today. At School 2, an SRS of 150 included 26 who missed breakfast today. There we have it. We have two populations, School 1, School 2. We have two samples, all right, one sample from each. This is going to be a two-sample z-test. Well, I guess it could be a two-sample z-interval. We don't know if we're doing a test yet, do we? So let's keep reading. More than 1,500 students attend each school. Do these data give convincing evidence of a difference in the population proportions at the alpha 0.05 significance level? Now we know this is a z-test, not a z-interval. All right, we're doing a hypothesis test, not a confidence interval. State appropriate hypotheses for performing a significance test. Be sure to define the parameters of interest, and we're going to go ahead and go through the entire procedure here. So, first things first here. All right, we want to test so our null, in this case, our null hypothesis is that the two proportions are the same, okay? That P1 minus P2 is equal to 0. All right, if they're the same, when we subtract them, when we combine them, we get 0. Another way, our alternative hypothesis is that they are not the same. So if we combine them, P1 minus P2 will not be 0. We don't think one school is bigger than the other. I mean, that's a possibility in problems like this. It could be greater than or less than. But this, we just think either they're equal or they are not. So this is actually going to be a two-tail test, but we will get to that later. Now, we introduced some variables, so we need to make sure that we define those variables. So where P1 is the true proportion of students at School 1 who did not eat breakfast, right? Today. So I'm just defining the two variables that I used. And P2 is the true proportion of students at School 2 who did not eat breakfast today. So we defined our two variables, and just to be safe, we will test this at a alpha equals 0.05 level. Ooh, there we go. Hopefully most of that looks familiar to you. All right. The only difference is that we are subtracting these two proportions now. All right. Our plan. All right. Here is what is our plan here? we are going to do a 2-sample z-test for P1 minus P2. All right, for the difference in proportion. Now, are we allowed to do that procedure? So we got to check our conditions. First, the random condition. Do we have 2 random samples? So yes, we have 2 random samples. All right, an SRS of 80, right? It was 80 of 80 from school 1 and an SRS of 150 from school 2. All right, random condition has been checked. Oh, actually, I forgot one of the most important words. Wow. I'm going to highlight this word because it's different. We have 2 independent random samples. Okay, that is the one difference here between a 1-sample and a 2-sample test. You need to put that word independent in there. All right, our 2 populations need to be independent of one another. So our 2 samples, the samples as a whole, need to be independent from one another. Okay, in order for this to be combined with all the math that we're learning, they need to be independent random samples. That just makes sure that you're not drawing from the same population kind of thing. All right, next is our 10% condition. All right, are we sampling less than 10% from each population? So in this case, we don't have to assume this. They tell us right here that more than 1,500 students attend each school. So we don't have to assume we are sampling less than 10%. We know 150, well, is exactly 10% of, well, it says more than, so it is less than 10%, and the 80 is also certainly less than 10%. Okay, so yes, both our samples are less than 10% of their respective populations in school 1 and school 2, because we are told both schools have more than 1,500 students. Little big for elementary school, but they tell us that's the truth, so that's what we are going with. And last but not least, the large counts condition. All right, this one is a little bit different, okay? There's a little bit more to the calculation here. We're still doing an n times p and n times q, all right? But it's the proportion that we use in that calculation that's a little bit different. So what we do is we find the combined p hat. Okay, we use the combined p hat. Whoa, sorry, my computer's wigging out right now a little bit. Come back to me, there we go. Nope, it's dying on me again. The combined proportion here. Now, why do we do this? Well, I think it's because of our null. Our null hypothesis is that there is no difference between P1 and P2. There's no difference between them. So we treat them as one sample when we're doing the large counts condition, okay? So how many successes do we have? Not that it's successful for students not to eat breakfast, but we have 19 in the first sample and 26 in the second one. So 19 plus 26, so that's my total number of kids that didn't eat breakfast, divided by my total sample size, which is 80. I'm going to pause this real quick. All right, hopefully that helps me. Sorry, I was having a really hard time writing here. 80 plus 150, that is my total sample size, right? So in total, we have 19 plus 26, which is 30, 45, out of a total of 230. This is our combined p-hat, which gives us, I'm on calculator. There we go. 45 divided by 230. A total combined p-hat of 19.5%. 0.19, let's go 196. Round that up there. And so this is what we're going to use for our P and Q for all the samples. Okay, so for school 1, we'll do 0.196 times 80, and we'll do 0.196. Oops, sorry, not 0.196. What's the Q? So 1 minus 0.196, 0.804. And we'll check to make sure both of those are greater than 10. And then we'll do the same thing for the other sample, 0.196 times 150, and 0.804 times 150. We'll make sure all of those are greater than 10. Remember, we got to do this for both samples. So 0.196 times 80, and 0.804 times 80. So 15, so about 16 and 64. Those are both greater than or equal to 10. Check and check. And our last one, 0.196 times 150, and 0.196 times 150. What did I, 0.804 times 150. There we go, bolt. So we have about 29 and 121. Those are both greater than or equal to 10. Check and check. Again, that's the same as usual, right? P times Q, checking our large counts. But yes, because this is the weird part here, we do calculate this combined proportion. We imagine if we combined the samples, okay? I've got a quick table up here. If you, at the top right, if we actually looked at the data, right, for school 1 and school 2, all right, how many total successes and failures were there? If we combine them, there were 45 yeses out of 230 as our total sample size if we sort of combined them, okay? But I think this fraction, instead of the table, I think this fraction's not too hard to remember. All right, well, now that we've checked all the conditions, we are allowed to do a 2-sample z-test for P1 minus P2. All right, and our calculator is just going to do this. You could build the sampling distribution if you wanted to and find the boundaries and do a normal CDF off of those boundaries, but it is much easier just to go stat, tests, oops, what am I doing? Stat, test, and find the one we want. A 2-proportion z-test, a 2-prop z-test, right there. And what does it ask us for? So it asks us to put in the data for the 2 samples. So our first sample, there were 19 out of 80. In our second sample, there were 26 out of 150. Now, what was our alternative hypothesis? That P1 is not equal to P2. Okay? Our null is always going to be that they are the same. Okay? That they are the same. Our second one is that they are not equal to each other. They're not equal to 0 if you subtract them. So I can either calculate or draw. I think I like the draw feature because that way it sort of shows you that we are doing a normal CDF. All right. And our p-value is 0.24, I'll round up to 0.243. And it's not a bad idea to put the z as well, 1.17. If you wanted to draw the normal model as well and color it in, that's also great for showing your work as well. All right, time for our conclusion. So let me make my window a little bit bigger. So because our p-value of 0.243 is greater than alpha, which is equal to 0.05, right? That's a really big p-value. The difference we see here is not surprising at all. We fail to reject the null hypothesis that P1 minus P2 is equal to 0, that there is no difference, all right? We do not have convincing evidence that the true proportion of students from school one, again, I'm just throwing the context. I'm saying what is P1, I'm saying what is P2, and I'm saying that we don't have evidence to say that they're different. The true proportion of students from school 1 who did not eat breakfast today. So we do not have convincing evidence that that is different from the true proportion of students from school 2 who did not eat breakfast today. Whew. It's a long sentence, but hopefully that sentence really is sounding formulaic. Okay? I'm not making up tons of new things. Most of that is just me copying from the problem, right? So we do not have convincing evidence that the first one is different from the second one. That's what we were testing, okay? All right. I'm hoping you see that that's very similar to what we've done in the past. A few small differences. All right, I highlighted them here for us. We do need to find the combined proportion when we're doing the large counts. We do need to add the word independent when we check our random condition because we have independent random samples. The two samples need to be independent from each other. And that's it. That's the only difference there. So let's take a look at one more quick example here. We're not going to actually do it. We're just going to read through it, okay? And because this one also has a few slight differences because it is an experiment. And so I want to highlight those differences, but we're not going to actually do the whole thing ourselves. So high levels of cholesterol in the blood are associated with a higher risk of heart attacks. Will using a drug to lower blood pressure or lower blood cholesterol reduce heart attacks? The Helsinki Heart Study recruited middle-aged men with high cholesterol but no history of other serious medical conditions to investigate this question. The volunteer subjects were assigned at random to one of two treatments. 2051 took the drug gemfibrozil to reduce their cholesterol levels, and a control group of 2,030 men took a placebo. During the next 5 years, 56 in the first group, the gemfibrozil group, and 84 men in the placebo group had heart attacks. So first, do they give convincing evidence at the alpha 0.01 level that it's effective in preventing heart attacks? And then interpret the p-value at the very end. So, first, our hypotheses. So the first, our null, is that there is no difference. If I take the first proportion and subtract the second proportion, you get 0. There's no difference. All right. Another one is that there is a difference. That the gemfibrozil group minus the placebo group, all right, G for gemfibrozil, PL for placebo, is less than 0, which we think the proportion for the treatment is going to be smaller amount of heart attacks, right? That's why small minus big will be a negative number, less than 0. Then they give us the context here, where P sub G is the true heart attack rate. You don't want to say number of heart attacks here, because these are proportions. That's important to note. For middle-aged men like these who take gemfibrozil. And P sub PL is the true proportion for men like these. Ooh, I like this. Men like these. That's important in an experiment, right? Who take a placebo using alpha 0.01. So they define the two variables. Plan, they're going to do a 2-sample z-test for P sub G minus P sub PL. All right, they use their variables there. So the first key difference I want us to see here is in the random condition. These were volunteers. We do not have a random sample. You can't do that for an experiment. All right. So where does the random come in? We randomly assign the volunteers. That's our randomness right there, okay? We have to have some randomness. Now, again, we are not taking these results and applying them to the population. All right, we didn't take a random sample. We can't apply this to the entire population. We can only apply it to, that's why this phrase right here was important, men like these. All right, not all men in the United States, not all people in the United States, just men like these. Important distinctions in an experiment versus a random sample. But large counts is the same. They make the combined probability here. Okay, so they get the combined p-hat, just like we did. Then they check their large counts, same way we did. They're all greater than 10. Looks good. Now, in the book, they definitely do this the hard way. Look at all that. So, yeah, brutal. You can do these long procedures by hand, making a normal model and then doing the normal CDF down here, or you could just do this part right here. Do a 2-prop z-test on the calculator. Report the z, report the p. Done and done. Then our conclusion, because this is much less than alpha, the p-value is much less than alpha, we reject the null. There is convincing evidence of a lower heart attack rate for middle-aged men who take gemfibrozil than those who take only a placebo. I'm hoping you saw a few key differences there between a random sampling survey versus an experiment. There were just a couple of differences there. Where was it? Our random, we have to randomly assign people. We do not have a random sample. We randomly assign. You want to make sure you don't imply this works for an entire population. All right, that's kind of dangerous. It is not for the entire population. It's just for people like those in the sample. And might as well take a look at, one more time, this sentence for what the p-value actually means. The p-value is assuming the null hypothesis is true. Okay, then they give us context that there is no difference in the effectiveness of the two treatments. Assuming the null is true, there is a 0.68 probability of getting a difference in heart attack rate for the two groups of this or less. All right, so they actually had to calculate that number. We didn't do it. We let the calculator do all that stuff for us, but they actually did P1 minus P2 and got 0.0141. So P1 would be 56 over that sample, and the other one would be this one over that sample, right? They actually calculated out the difference in proportion of getting 0.0141 or less just by the chance involved in the random assignment. Sample variability, essentially, right? There was a 0.014 probability of that happening by random chance. That is crazy small. So we reject the null hypothesis. Okay? Sorry, there was a 0.006 probability of that happening. So we reject the null. But it's been a while since we've written the p-value sentence, so there is a good example. All right, I hope you can see the difference between a one-sample z-test and a two-sample z-test, and how that can then be applied to experiments.